Welcome to complex analysis. This is the series of lectures on the main results of holomorphic functions, second session. Today we shall be dealing with the so-called identity theorem, and that's a very significant important result, and we'll also look at the ways how to use it. Okay, we'll also bring out the significance of such a result. Let's get started. See, in mathematics, one of the main results is, suppose I have two functions f and g from a set x to y. These are sets. Okay, then we say f equal to g if and only for all x in x. Okay, fx must be equal to gx. Okay, right. So if x is very large, then to check f equal to g, we have to check very many conditions fx equal to gx for each and every x in x, right? But if x and y have additional structures and f and g also have additional properties, then we may cut down our work. Instead of checking for all x in x fx equal to gx, we may be able to reduce our work. Okay, what do I mean by that? Let us look at some examples. Okay, the first example, suppose f and g are polynomials. Okay, c to c are okay, let us say c to c polynomial. That is, these are polynomial functions fx equal to something. Okay, akx power k equal to 0 to m, and gx equal to bk x power k, and here 0 is 0 to some n. Suppose n is greater than equal to m, then when I want to say f equal to fx equal to gx, okay, as if I consider as functions, okay, then for each and every z in C, I have to check fz equal to gz. But we know that since n is the maximum degree, if I have, let's say, alpha 1 to alpha n plus 1 element, if f alpha j equal to g alpha j for 1j less than equal to j less than equal to n plus 1, then I know f of z is g of z for all z in C. How do I know that? Because that means, look at the polynomial f minus g. This polynomial is of degree at most less than or equal to n, and it vanishes that it has n plus 1 roots, namely alpha 1 to alpha n plus 1. That means it must be 0 polynomial, etc. Right? Okay. Second example, this is algebra, but we turn it analysis kind of thing. Okay. Suppose now I have f and g are linear maps from v to w. Linear. Okay. F and v and w are vector spaces, right? Then we know that if b is a basis of v, then if I check f of v equal to g of v for all b in the basis, then f equal to g on v, right? In particular, if v is finite dimensional, then I only have to check equality. To show f equal to g, I only have to check f of vi equal to g of vi, where v1, v2, vn is a basis, right? And suppose B is a vector space over R and is a positive dimension, right? Okay, then the set V as a set is infinite. It's uncountable. So I don't have to check. I just have to check the equality for linear maps f and g only at a finite number of points, right? Now come to analysis. Suppose I have two continuous functions from, let's say, R to R. Okay, right? And to check continuous f equal to g for each and every x in R, I have to check fx equal to gx. That is uncountably many conditions. But we know that if I take q, this is a countable dense set, right? So if I know fx equal to gx for all x in q, then I know f equal to g. This is analysis. Yeah, keep these things in mind, right? So the question I want to know, there are a few more I can say, but this is good enough for us for the time being, right? Okay, let us look at. So suppose I have a power series f, okay, f of z equal to, let us say, cn z minus a to the power n, g of z equal to dn z minus a to the power n. This is valid, okay, on a disk of radius r, bar. Okay, so these are functions now. F and g are functions. I want to know when these power functions are equal. Okay, right. So the obvious thing is I would like to say Cn equal to Dn, right? But think of it a slightly different way. For simplicity, let us assume f of z equal to, notice that if I look at f minus g, that's again a power series. Cn minus Dn into z minus a to the power n. Therefore, this as a function is 0, is same as saying Cn minus Dn is 0 for all n. That means Cn equal to Dn, right? Okay, right. So now if, suppose I assume this is this z b0 r. Now I want to know when this is a 0 power series. That means it is 0 z power n from 0 to infinity, right? Okay, intuitively I can think of, just for fun, okay, don't laugh at me, and if you say, you may be laughed at, but just for intuition I can think of this, yeah, this power series as a polynomial of infinite degree, right? So what should I expect? So if it's a polynomial infinite degree, if I add one more, if it vanishes at infinity plus 1 point, it must be 0, but that doesn't make sense. Infinity plus 1 will be again infinity. Okay, but we are doing analysis that gives us another. So let us assume my f of z is summation Cn z power n, and disk of convergence is B0R. Let us assume there exists zk sequence in B0R, so that zk is different from 0 and zk converges to 0. Then, okay, that means the power series vanishes at infinitely many points, okay, other than 0, right? Then I want to know whether f is the 0 power series. That means same as saying all for all n Cn is 0. Okay, this is the question we want to ask, right? Now f is continuous on B0R. Therefore, f of 0 is limit of f of zk, but that is 0. But f of 0 is a0. Therefore, we have proved, sorry, c0. c0 is 0, right? So my idea is to, by induction, to prove all my Cn's are 0. I want to prove by induction Cn's are 0. So let us assume C0 equal to C1 equal to Cn, Cn minus 1 equal to 0. So now to prove Cn is 0, right? Now let us write what is f of z. F of z is summation C k z power k is greater than or equal to n. Therefore I can write it as z power n into summation C n plus k z power k equal to 0 to infinity. Okay, this I will write as z power into g of z, where g of z is this object. Okay, note that this series is convergent. This is a power series. Don't worry about n plus k, call it as dk z power k. This is convergent. Why it's convergent? I know this is convergent. Okay, right? Now let's look at, if I have a series, okay, I will use some other notation perhaps. Suppose an is convergent, okay, and alpha is non. If I know alpha an is convergent and alpha is non-zero, then I have summation. I know these are equal, right? And since alpha is non-zero, I get this is convergent. This series is convergent. Do you understand this? So here z power n is common. If z is not equal to 0, okay, this series is convergent. But if z is equal to 0, then the only surviving term is going to be Cn. Do you understand that? Therefore, the series is convergent. Please understand. Okay. And therefore, g of z, which is equal to summation of this series Cn plus k z power k equal to 0 to infinity, this is continuous. Okay, on B0 R. It may even converge on a larger thing, but at least it on B0 R. Okay. Now what is that I want to prove? I want to prove Cn is 0. Right. So I want to make use of an alternate description of Gz. Now notice that Gz is nothing else than f of z by z power n. If n is z is not equal to 0 and z is in B0 R. Right. And what is G0? That is of course Cn at z equal to 0. Is that clear? That's our definition. Right. Okay. Now what do I want to prove? Cn is 0. Therefore, what should I prove? Limit z going to 0 of g of z is g of 0. Okay. I want to prove this. This is Cn. So if I want to prove Cn is 0, I have to prove this limit is 0. Now I know the limit exists because g is continuous. Right. Therefore, let us look at a sequence zk which converges to 0, which is given to me. Right. And what do I know? Then g of zk is f of zk by zk power n, but this is 0 by zk power n because remember zk's are non-zero. Therefore, this is 0. You understand? Yeah. Therefore, limit z going to 0 of g of z is same as I can compute using in particular equal. Okay. There is a same as a limit zk going to 0 of g of z, which is 0. Right. Therefore, I have proved Cn is 0. Okay. Make sure you understand. Okay. Limit is 0. Therefore, for any sequence zn zk converging 0, g of zk must be the same limit. Right. And uniqueness of the limit will say the limits are the same. But g of zk's are 0 for each and every k. Therefore, the limit z going to 0 of gz is 0. But that by continuity that must be g0. But g0 is Cn. Therefore, Cn is 0. Okay. So what I have shown? So by induction. So PRP. Make sure that you understand this logic. Therefore, for all n, Cn is 0. That means f is identically 0. Okay. This is called the theorem. What the theorem which you proved is uniqueness theorem for power series. So what does it say? Let f of z be a power series. Okay. Cn z minus a power n equal to 0 to infinity with a disk of convergence BAR. Assume that there is a sequence zk in BAR so that zk is different from a and zk converges to a, and okay, f of zk is 0 for all k. Then f is 0 on B0 or BAR, sorry. Okay. I have assumed a is 0 and proved, but the proof is the same. For example, what will be? G of z will be some c n plus k z minus a to the power k, etc. Okay. Therefore, my f of z will be, sorry, g of z will be f of z by z minus a to the power n. Okay. The argument is the same. Okay. Understand this. Okay. Even though I proved for the standard power, this power center of power series being taken as a equal to 0. Now suppose I have two things, okay? As I said, Cn z minus a to the power n and Dn z minus a to the power n, both converging in VAR, and suppose I have zk, no, okay, and zk converges to a, and okay, and f of zk equal to g of zk for all k, then that will imply f must be g on VAR. Is that clear? Because I only have to consider the power series Cn minus Dn into z minus a to the power n. Notice that this is conversion, therefore their difference is also conversion by algebra convergence series. Okay, and this is a convergent power series, the radius disk, okay, which converges on the disk here. Okay, now apply the last result. Okay, call this if you want phi of z. Okay, then what do I know? Phi of zk is 0 for all k, and zk converges to a, right? Therefore I know phi is identically 0, etc, etc, etc. Yeah, so the general result is proved. Okay, so what did we finally achieve? Oh, good, I am sharing the screen. I was a little worried. What have we finally shown? We have shown if I have two power series, they are equal. Okay, to check they are equal, I don't have to verify f of z equal to g of z for every z in the disk of convergence, common disk of convergence. What all I have to do is look for a sequence of points zk where zk is different from the center of the power series a, but zk converges to a. If f of zk equal to g of zk for all k, then f equal to g. You see that? Please understand this in view of my earlier remarks, the starting remarks which I gave you examples. Okay, we have simplified. You will be very surprised. Just a very far reaching consequence we will see in a minute. Before that, I just want to make an observation. This will also come later, but this is easier. The same proof will show. Okay, assume that as usual f of z equal to summation Cn z minus a to the power n, etc, etc. Okay, VAR. Okay, I want to say the if f is not identically 0, is not 0, okay, then the zeros of f are isolated. What does it mean? Okay, what does it mean? What does it mean is the following. So let us look at, suppose I have a topological space or a metric space. The proof is the same. I say a point P in X is isolated if there is an R positive such that BP of R is has only one point. Okay, in the topology there is an open set containing P, but that open set consists of only one point, namely P. Okay, so what does this mean here? So if I say, let's say Z0 is a 0 of this, f of Z0 equal to 0, then I want to say there is an R positive such that on BZ0 of R, if you start with any Z here, f of Z is not equal to 0. Okay, what is the, do you understand what I am saying? Suppose Z0 is in BAR such that f of Z0 is 0, then there exists, I want to prove this. There is an R positive such that for every Z in BZ0 of R, f of Z is not equal to 0 if of course Z not equal to Z0. Okay, so here it may, of course the function vanishes here, but at all other points it does not vanish. Okay, keep the picture in mind. Okay, the proof exactly the similar lines. Okay, suppose z0 is a 0 of f. That means f of z0 is 0, right? Therefore, I can write this f of z. Okay, do I want it? Okay, so in a neighborhood of z0, let me write it as a power series. Okay, Cn z minus z0 power n. Okay, so this is BAR, and then I have this, and we have seen any power series function is analytic. Therefore, there is a some other R, so that B z0 of R is contained in BAR, and therefore I can write it as maybe it's a DN. Okay, I want to prove that. Okay, right. Now notice that f of z0 is d0, therefore that is 0, right? Therefore let, okay, n be the first non-zero integer, so that, okay, integer k, so that dk is not equal to 0. That is d1, d2, dn minus 1 are 0, d0, d1, dn are 0, but dn is not 0. Therefore I can write f of z as, okay, dn z power n, dn plus 1, z power n plus 1, okay, maybe z minus z naught, and so on, right? So like last time, I can take out this and this, dn plus k, z minus z naught power k, k equal to 0 to infinity, right? And call this as gz as earlier, right? So what is g of z naught? G of z naught is, okay, dn, and dn is non-zero, right? Now as I observed earlier, g is continuous, and g of z naught is dn not equal to 0. That means there is an r positive, so that, okay, and maybe call it rho, b z naught rho, okay, for every z here, g of z is not equal to 0, right? So this is my z non-zero, this is my dn, okay. Therefore choose and discard on this, so that this does not contain origin, call it as v. Then g inverse of v will be an open set which contains z naught, and therefore there exists an open ball g b z naught of rho which is contained in here, okay, and therefore the image for every point z here, g of z lie in this open disk, therefore it cannot be 0. Okay, this should be very easy. I am sorry if you are missing, that means your basic topology is weak. Please learn that carefully. Is that okay? G of z is not equal to 0, right? Now what is f of z? F of z is z minus z naught into g of z. Therefore z is not equal to z naught. This is non-zero, and we know this is also non-zero for all z in b z naught rho, right? Therefore I have proved there exists a rho positive, so that on b z naught rho, the only 0 of f is z naught. Okay, pause, review, proceed. Okay, next we are ready to prove this identity theorem. To prove identity theorem, let us do very small steps. Okay, yeah. So what is the theorem says? The identity theorem, let me state it. I am going to ignore an important condition, but toward the end of the proof you will know I have to put that extra condition. Okay, you will supply that condition. Okay, let U be non-empty open set, right, and F is holomorphic to C, right. Now what I want to assume is that there exists Zk, okay, a sequence such that f of Zk is 0 for all k. Yeah, and let me also assume Zk converges to some Z0 and Zk's are different from Z0. Then I want to say f is identically 0 on U. This is exactly like what we said about power series. Do you understand that? Yes? Okay. So let us look at. We will work through a proof. So what do we know? I have a sequence Zk so that Zk's are different from Z0 and f of Zk converges to, sorry, f of Zk's are 0 for all k. Right? Therefore I know f of Z0 is also 0 because f is continuous. Right? Now let us expand. Remember, f is holomorphic, therefore I know there is a on some b z0 of R which is contained in U, there is a power series expansion. F of z is going to be Cn z minus z0 power n from 0 to infinity, and for all z in b z0 of R, b z0 of R. Right? Therefore, what we have concluded is f of z0 equal to c0 is 0. Right? Okay. But let's forget it. Now let's look at this is a power series, right? And since zk converges to z0, okay, there is an n such that for k greater than or equal to n, all my zk will lie in b z0 of R. Right? Therefore, I have a sequence zk k greater than or equal to n, and this sequence zk, they are all different from z0, and it converges to z0. Right? Therefore, by the uniqueness of power series, we know that all my Cn's are 0 by the last result. Okay, just make sure you understand this. Yeah, but what are Cn's? Remember, see, okay, but what are Cn's? Because that is very important for our learning. We know that Cn's are nothing other than nth derivative at z0 by n factorial. Therefore, it simply says nth factorial of z0 is 0 for all n. Yeah, right. So this is going to give us a way of attack. So pause, review, proceed. So let us look at E to be the set of Z in U so that its nth derivative at Z is 0 for all n in Z plus. Right? So this is non-empty. Why? Z not belong to E. Just now we proved. Right? And notice that E is automatically open. Why E is open? Because suppose A belong to E, right? Then Fn of U is 0 for all nz plus, right? That means, yeah, okay. Let me look at any R so that Br is contained in U. Then I know I have a power series expansion of Fz there, right? Are you following? That is F at n at A by n factorial z minus a to the power n, etc., right? Okay. Oh, this is for z in Br. Okay. That means this function f is identically 0 on Bar. Please look at the subtle argument. Okay. You understood? When I want to say E is open, what I want to show is let A be there. I have to show that there is an open set or there is an open disk, okay, centered at A, which is contained in E. I am going to claim this is contained in Bar is contained in E. Okay, I want to claim this. Okay, how am I going to claim? What I noticed is under the stated assumption my F is going to be 0 on this Bar, right? Because this is going to be the Taylor series expansion or the power series expansion of F on this. Okay, because we know any holomorphic function admits a power series expansion, Taylor expansion. Therefore, it is going to be 0, right? Now you start with any, okay, let me call some name B in Bar, right? Then what? There is some row so that B row is contained in Bar, and on that, okay, I have a power series expansion, namely f at of n by b by n factorial z minus b power n, etc. But this function, this is f of z for z here. But I know this f of z is 0 because b row is contained in Bar, but on Bar f is 0, therefore this is 0. That means my fn of b is 0 for all n in z plus. That means, okay, b belong to E, and b was any arbitrary point of Bar. That means Bar is contained in E. Okay, this is a very tricky argument, not straightforward, but if you are a beginner you may get confused. Just make sure. Okay, therefore E is non-empty and E is open, and E is closed. That's very trivial. Why E is closed? Why? Notice that E is intersection of, okay, nth derivative, okay, this is a function, it's inverse of 0, right? This set of all points z so that n varies over 0 to infinity, right? Now remember, f is holomorphic, therefore f, it's infinitely differential, therefore this is continuous. Here any nth derivative is continuous, and 0 is a closed subset. By continuity this must be a closed subset, okay, in U, right? But intersection of closed sets is closed, therefore E is closed. Therefore E is not empty, open and closed in U. Therefore I want to say E equal to U. When can I say this? I know all of you know, right? If U is connected. So let's go back to the theorem. So open and connected. Okay, let's quickly recall what did we say. F is U to C, U is open and connected, right? And there exists zk in U and zk converges to z0, that is in U, right? Remember what did we want? I hope I mentioned that. Yeah, z naught in u. This is very. Why did I need z naught is in u? Because we want to write power series expansion around z naught. Okay, if z naught is in u only, then I can write it. Z naught belong to u. Therefore, there is a r positive such that b z naught r is contained in that. So this is a very crucial statement. Okay, such that zk and z naught is in u. Okay. Okay, this z is in u or z naught if you want. Then and f of z naught is 0, zn is 0, zk is 0 for all k. Then f is identically 0. F is 0 function, right? This is the theorem I proved. Okay. There are various ways of formulating the theorem. There are various consequences, immediate consequences. Sometimes it may be needed, sometimes it may not be needed. Suppose I have an open set, connected open set U. Okay. Suppose I have an arc like this. Okay. And suppose my f is 0 on this. Right. Then f is 0 on U. Why? Because when you think of arc, think of this as some open interval AB to U perhaps. It's a continuous thing. Then for each t in AB, you have gamma t, f of gamma t is 0 for all t in AB. Right? You understand? Now start with any t naught, a less than b less than t naught. Then for sufficiently large, okay, k, if k is very very large, t naught plus k will be less than b. And t naught plus 1 by k, call this as tk. Similarly, t naught 1 minus k, that converges to t naught. Right? And remember, t naught is still in AB. Therefore, f of gamma tk is 0 and this converges. You call it as zk, and gamma t naught you call it as z naught. Okay, zk converges to z naught because gamma is continuous. Tk converges to t naught. Therefore, gamma tk converges to gamma t naught. That means zk converges to z naught. Right? Are you following? Okay. So these are the typical situations. Okay. Now let's look at a standard version of the identity theorem, which is also stated in my book. Let f from u to c be holomorphic. Let me just make sure I'm sharing. And u of course open and connected. And f is okay. And let's look at 0 set of f. This set of all points z in u so that f of z equal to 0. Okay. Then if there exists z naught in u so that z naught is a cluster point of zf, then f is 0 on u. This is standard version. Okay, the proof is easy. Now notice that z naught belongs to u, right? That's a very crucial point. Where is z naught? It has a cluster point inside the domain. Okay, now z naught belongs to u. Now it's a cluster point of zf. That means there exists a sequence zk in z of f, the 0 set, so that zk's are different from 0. and zk, f of zk equal to 0, and zk converges to z0 because z0 is a cluster point, right? Yeah, in case you had forgotten your definition of cluster point, I don't use the word limit point, I'll use only cluster point. Okay, so okay, x0 is a cluster point of a set A in a topological space x tau if for every open set u containing x0, u intersection A, okay, contains a point other than A, other than x0. In the case of metric space, for every open ball bx0 or intersection A contains a point other than x0. x0 may or may not be there. Okay, right. Okay, but then by identity theorem, as I said, f is identically 0. Okay, so we proved the result. Okay, as an immediate thing, a typical way of using this will be like this. Suppose f from u to c holomorphic, a typical use. In fact, we will need it later, holomorphic, and suppose u is as usual connected plus open, right? Suppose B is non-empty, open, V contained in U, and suppose F is 0 on B. Then I want to claim F is 0 on U. Okay, that's because in Euclidean spaces, okay, if, okay, this is a very general remark, a topological remark actually. If, okay, if B x, well, let us say BAR is an open set in any Rn or Cn, okay, right, then every x in BAR is a cluster point of BAR. This is very easy because you choose for n sufficiently large, you see x plus 1 by n times, let's say, E1, okay, right. In the case of R1, if you want only C, let us stick to C, so that okay, BAR in C, whatever argument I am giving will work earlier, I will just see, okay. Then every Z here is a cluster point of BAR. Why? Because if n is very very large, Z plus 1 by n will be in BAR, right? And therefore Z plus 1 by n, they are all different from, okay, A, okay, they are all different from Z, and Z plus 1 by n converge to Z. Yeah, to show it's a cluster point, what I have to show? In every neighborhood of Z, okay, neighborhood of Z, there exists a point of BAR other than this. Are you following? Okay, these are the points which are in BAR, right, and they converge to Z, and they are all distinct from Z, right? Therefore, this Z is a cluster point. Now we'll come back. Therefore, if F is 0 on V, since V is non-empty, there exists an A in V. Therefore, there exists a BAR contained in B. Therefore, F is 0 on BAR, right? Okay, but then there exists a sequence Zn in BAR, so that Zn converges to A, and Zns are different from A, and F of Zns are 0. Therefore, by identity theorem, F is 0 on U, because U is open and connected. Okay, And there is a very typical application which will be very needed. I'll go to the next page. That is this. Suppose f from u to c is non-constant, holomorphic, and u is open and connected. Right? Now for any a in u and for every lambda in c, there is an r positive so that BAR is contained in u, and for every z in BAR, z not equal to a, f of z is different from lambda. It looks very complicated, but it's not. That means 0 less than distance between z minus a less than r implies f of z is not equal to lambda. Okay. The proof is easy. Suppose false. Okay. So I can take r equal to something like 1 by n for n sufficiently large. Therefore BAR will be contained in my u. Right? So suppose false. That means on BA 1 by n there exists some Zn such that Zn is different from a, and such that f of Zn is lambda. Right? Okay. Now let's look at such Zn. Zns converge to a, and Zns are different from a, and if I look at the function g of z equal to f of z minus lambda, okay, then g of Zn are all 0. Zns are different from a, and Zn converge to a, therefore g is 0. Yeah, right. Okay, this is a function depend on u, is open and connected, therefore g is 0 on u, but that means f is lambda on u. That's a contradiction because we assume f is a non-constant holomorphic function. Okay. Just a remark. Okay, if I don't say that remark, I cannot sleep well. Okay, this result is significant only if f of a equal to lambda. Because if f of a is not equal to lambda, by continuity the result follows. Right? So I have f of a and lambda, therefore I can choose and open this, therefore this is my u, and there is an a, there I can choose something. This ball will be mapped by f to this, therefore all these points here will miss lambda. Right? So therefore the only thing is f of a equal to lambda. Okay, and this is where we used identity theorem. Okay, this is exactly the same thing which I said earlier. The zeros are isolated. Now let us look at that. If I define g of z equal to f of z minus lambda, and if f of a equal to lambda, okay, then that means a is a 0 of g, therefore it must be isolated. So there exists a neighborhood of a, open disk around a, on which g does not assume the value lambda except at a. This we had already seen. This is the same result, but this way of looking at it is very important. That's why I mentioned that. So please go through these things. This is one of the very basic results. These are all the main results. The theorem which we did, Moreira's theorem and identity theorem, and we will use it in the next session on maximum modulus principle. So please learn all these things well. Take care, stay safe, we will meet again.